So we've looked at vector differentiation, where similar to how we have scalar differentiation, where we saw that it is the change in the value of the function. So this change in value of function over a really small interval, with that small interval tending to zero, that was a scalar differentiation. And for vectors, we saw that it's the same idea expanded to vectors, where now there's a change in the vector divided by, in this case, a really small amount of time. So that was average velocity, similarly for average acceleration, and so on. And this vector differentiation does result in a direction that is defined in this way. So it's the change in the vector over some delta t time is given in this direction, and the magnitude of that would be the magnitude of this overall vector. Okay, and previously we saw the case with the unit vectors fixed, where we saw that if it is the case that your I hat, j hat, and k hat are always in the same direction and they do not rotate, in that case, the vector differentiation is simply the differentiation of the scalar values along each component, right? And this here was how we had done acceleration. Of course, you can do the same thing for position and so on. So we've done that over here, looking at how integration from acceleration will result in the velocity, integration from velocity will give you the position, and so on. So this is pretty straightforward. Let's now remove this assumption of the unit vectors being fixed, and let's see what happens then. So we can look at an alternate way of representing motion. If you have, your particle is moving in this way. Previously, we were looking at the case where you had a fixed I hat, j hat, and k hat. And so you would find this distance, then you'd find this position, which is this distance and this distance, and then you'd find this, and so on, right? But there's an alternate way of defining the position of a particle, where now what we do is we look at the radial distance. So let's say that this here is your reference, and you can look at the radial distance. So this distance is given by some r of t, and there's an angle with respect to a fixed axis, which is given by theta. So in this way, again, using two quantities, that is the angular position and the radial distance, you can define the position of the particle as it moves along its trajectory. So at this position, there's the distance and there's the angle. At this position, the angle is close to zero and this much is the distance. At this position, this is the angle and this is the radial distance, and so on. Okay, so this here would be called the polar coordinate system. You now have the position of this point or particle defined by some scalar value, that is this radial distance, and a direction that is in this way, right? So if you have this direction, a unit vector in this direction, and the magnitude r of t, you fully define the position as some r vector is equal to r, the scalar, and now you need a unit vector that's aligned along that radially outward direction, that is given by er hat. Okay, so here this er hat is the radial direction. Now the thing is, this radial direction, it keeps changing, right? So this is currently the position here. Let's say that is r1 of t, theta 1. At this position now, over here, it is some r2 of t and some theta 2 is also changing with time, right? So there's theta 1 of t, that is theta 2 of t. So that means that the position vector, which was originally this one, has now changed to this one. And the unit vector has rotated from this direction to this direction. Okay, So the rate of change of rotation of that unit vector is given by the angular velocity. So that here is the angular velocity omega vector is equal to theta dot in what direction? So here again, you want to have your right hand rule, which means that you have your fingers curling in this orientation. So if you do that, your thumb would be pointing outward, that's along the k hat direction. So this here is the case as shown. So this is theta dot k hat is your angular velocity. Of course, as an extension of that, angular acceleration, which is given by alpha vector, is equal to theta double dot k hat, or you might write this as alpha k hat, where alpha is a scalar value, and the above one as omega k hat, where omega is a scalar value. Okay, so this here is telling you how the unit vector er hat is rotating, and this er hat vector is dependent on theta, right? So if I were to mark it over here, it would be radially outward. Okay, I guess this is an important aspect. It should be radially outward from your reference. This is your ER hat at position 1, while later it has come to this position, this direction given by ER hat 2. Okay. The polar coordinate system uses another unit vector that is E theta hat, which is in the direction of increasing theta. So theta is increasing in this direction, right? So wherever you are, you have a perpendicular direction that could be either this way or this way. You choose the one in the direction of increasing theta, which would be this one. So this here is E theta hat 2. And in the other position, over here, you have E theta hat 1. That is called the transverse direction. So E theta hat is the transverse direction unit vector. It is perpendicular to E r hat and is in the direction of increasing theta. So why do we bother with creating such a coordinate system where your unit vectors are rotating in time? There are so many reasons. Most importantly, when you're tracking some object and you're able to calculate the radial distance and you know what is your angular position, then you can use that to determine its velocity and acceleration and so on. And we will get to that with some very interesting examples. But first, we need to make sure that we understand that there's a big difference between this system and what we looked at over here, where the unit vectors were fixed. In this case, every single instance of time, the position can be defined. So if it was over here, the position is defined along I hat, j hat, and k hat. So it was this, this, and this. And at this position, it was again defined along I hat, j hat, and k hat. It was this one, and this one, right? Now we're changing it to a different coordinate system where the unit vectors are rotating. So we have a magnitude r1 of t along this direction first, and then we have another magnitude r2 of t, which is along this direction now. Even though we have the magnitude, our unit vector er1 hat has now become er2 hat, which has rotated by some angle theta 2 minus theta 1. Okay, so important to keep in mind is that er hat is now dependent on theta, and the way that is dependent is based on this angular velocity and acceleration, which are quantities that can be measured by your tracking system, whether it's a camera or radar or something like that. Okay, so let's come back to this. R vector is r er hat. Now, if we were to obtain the velocity, it's not simply going to be r dot er hat, similar to what it was before, And the reason is because ER hat is now changing in direction as well. Right, so our objective now is how to obtain the velocity and the acceleration when ER hat is rotating. We cannot do velocity is equal to d over dt of r vector is equal to r dot ER hat. This is wrong because this would only work if ER hat was fixed. But now ER hat is rotating, and so you cannot simply do the differentiation of the magnitude, which is kind of what we saw in this process, is that you can just look at the differentiation of the component along each unit vector. We cannot do that anymore. Okay, so let's look at this a little carefully. Now going to sketch this in a little more detail. Well, actually, I can use the same. I just have to define infinitesimally small quantities. So I'm going to now write this as a function of time. So this here is r at time t plus dt. This here was r at time t. This here is er hat at the time t. This here is er hat at the time t plus dt. So I'm basically saying that in an infinitesimally small amount of time, this er hat has changed to this er hat. Similarly, for theta hat, we have t plus dt and e theta at time t, which essentially means that this here, if this was theta of t, then this here is d theta. Okay. I've just defined these new unit vectors as infinitesimally small changes from the previous unit vector. If I were to now expand upon this, by that what I mean is if I'm going to zoom in and I'm just going to look at the angles that are formed. So I'm going to try and create a zoomed in version. Okay, so I sped that up, but what I'm trying to show here is that all I've done is I've taken this and expanded it to this, the same direction. This one, expanded it to this. It's like a zoomed in version. And perpendicular to these are the corresponding unit vectors e theta hat, so that's a transverse direction. So perpendicular to this is e theta hat at time t plus dt. And perpendicular to this is e theta hat at time t. Okay, so once you have this, you can now look at the difference that is actually occurring. So here, if you were to look, this here is a difference in the ER hat vector, and this here is a difference in the E theta hat vector. So this is the infinitesimally small change happening in the ER hat vector over time t, over time dt, and there's a infinitesimally small amount of change in the E theta hat vector over time dt. Okay. The angle over here, what is that going to be? So we know that over here, the angle between these two is d theta. So you now have that this here is angle d theta. And if this angle is d theta and this angle is 90 degrees, then this has to be 90 minus d theta. And if this here is 90 degrees, then this has to be d theta again, right? So this is also d theta. That's the angle in between these infinitesimally small changes in the unit vectors. Okay, now let's look at what is the magnitude of these. Okay, so what can we say here? Um, if you think of this as a unit vector which has a magnitude of 1 that has rotated by an angle of d theta to come to this point, and the arc length over here would be r d theta, right? So this here is a radius r, is rotated by d theta and it's come here, the same r. And so the arc length would be r d theta. But the problem is that this r is equal to 1. And so the magnitude of this arc here would be d theta. And if the it was an infinitesimally small amount of change, that arc can be approximated to be this distance over here. So this here is going to be the magnitude of DER hat. Okay, that was me explaining it in words. If I were to sketch a circle here, it is like you have this unit vector. Let's say it is ER hat. It is now rotated to this position here. Is ER hat at time t plus dt. I'm saying that this arc length is equal to r d theta, since this is here d theta, and since it's a unit vector, okay, so this means that the arc length here is going to be equal to d theta, and for infinitesimally small rotation, the arc can be approximated to be a straight line. Or in the terms of circles, this would be the chord. Okay, so the magnitude of DER hat is equal to d theta according to this entire argument. So this here, this magnitude of this vector here is equal to d theta. Okay, extending this to the idea for E theta hat rotating by d theta to get to this point, and the magnitude of this is also equal to d theta, simply because this is the angle subtended between these two rotating vectors. So at this point, we have defined the magnitudes of the changes, that is DER hat and DE theta hat. And what about the vector in itself? First, this here is a unit vector, ER hat, but DER hat is not a unit vector. It is a vector that's oriented in this way. The magnitude is what we just defined here. Similarly, this here is not a unit vector, is a change in the unit vector. That magnitude is defined here, and the direction is in this way. We now have to define the directions. So essentially, DER hat is equal to, we have the magnitude, and then we have to think about the directions. So DER hat, you can write that this is aligned along E theta hat. So we can write it in this way, especially for an infinitesimally small amount of change. This would be aligned along E theta hat. It will be perpendicular to the change, it will be perpendicular to the original unit vector. And similarly, d E theta hat would be equal to the magnitude times what is the direction? This direction is opposed to this ER hat direction. So it is minus ER hat direction. Okay, so this is what we have kind of defined in this geometric analysis of unit vectors rotating. And let's now apply this to then find out how we can differentiate the position vector given by r is equal to r e r hat, right? But this here was a scalar, and this here was a rotating unit vector. So what is v? The differentiation of the r vector. Essentially, we have this as your r vector becoming this in time. What is the rate of change of that position vector? That gives us the velocity, right? So this is now the differentiation of r er hat, which you can treat as two quantities. One is a scalar, one is a unit vector, and we can apply the product rule. So you get d dt of r in the er hat direction plus r d dt er hat. Okay, so in this case, this is the product rule that we just applied. This is just r dot. And here we have r der hat over dt. Now we can take der hat from this above to write it as d theta dt with e theta hat as the direction. Right? We just replaced der hat with this. And in the end, this gives us r dot er hat plus r. What is d theta dt? It's by definition r omega. That's the angular velocity. So this is r omega e theta hat. Okay, or r theta dot e theta hat. This is the velocity of a body that is captured in polar coordinates. Okay, I hope this makes sense. Let's now apply the same method now to obtain acceleration. In this case, acceleration is a differentiation of velocity. Why don't you give it a shot? Try doing the same approach that I did above over here. You're just going to replace every differentiation der hat dt. You're going to replace it with d theta dt and so on. Okay, you can pause and come back. I will continue now. Okay, so it is the differentiation of r dot er hat plus r theta dot e theta hat, which if you were to now apply the product rule, you can do it as d dt of r dot er hat plus r dot d dt of er hat. That is the first term, product rule. And then I have now this, you have to apply the product rule carefully. You will have the differentiation of, we can do r theta dot in e theta hat plus, keep this constant, and you have d dt e theta hat. Now the first one becomes r double dot er hat. Second one becomes r dot. Now this infinitesimally small differential quantity can be replaced with this. So you have d theta dt, so that is theta dot e theta hat. And then now you have this here. It's a scalar product rule. So then you have r dot theta dot plus r theta double dot in e theta hat direction. And then you have r theta dot. Differentiation of e theta hat becomes d theta minus er hat. So that is theta dot minus er hat. If you now were to combine all the terms, collect all the er hat terms first, you should get r double dot minus r theta dot squared er hat plus you get 2 r dot theta dot plus r theta double dot e theta hat. So this here is the acceleration in polar coordinates. If this is too abstract, let's do a problem that makes it clear what all of this means. Okay. First, maybe a numerical problem. A particle is being trapped in polar coordinates, and it is found that theta is equal to 0.2 t plus 0.02 t cubed, and r is equal to 0.2 plus 0.04 t squared. Okay, what does this mean? It means that from some reference, this particle is at some time t, its radial distance r is defined according to this. Okay, so this is r of t, and at some time, at that same time instance, the angle that's being measured is given by this over here. So you can vary the time from 0, 0.1, 0.2, 0.3, and so on, and you'd be able to get a trajectory that defines how this particle is moving in space. Okay. Now, in the polar coordinate, that means that your ER hat vector is rotating, and how it rotates is based on this theta, and your magnitude, that is how far are you from the point from where you're making these measurements, is changing according to this. Okay, think of where this could be used. You might have a camera that is tracking a car that's driving across the road. That car, its radial distance is obtained using perhaps radar or laser. That's kind of how speed cameras work. And as the car is moving, this theta is changing according to this. Another possibility is you have some aircraft that is flying and you have a radar positioned here. So your radar station is now tracking the aircraft. It's initially looking in this direction to capture the aircraft at this position. The radar tells you what is the distance. And then as it moves to this position, you have a different angle, this angle here. And the radar tells you this is the new distance. So that's the radial measurement. And you have another position here and so on. So as the radar keeps sending out these blips to obtain the position, you get different thetas and r's. Okay, another case, a submarine, as it is going at the close to the ocean floor, you have a ship that is sending out radar signals, and it's able to capture the position of this submarine as it is moving underneath the ship. So many practical applications where this kind of a coordinate system works really well with the way that measurements are being taken. Okay, so now this here is your theta and your r. And the question then asks you to obtain the velocity and acceleration at t is equal to 3 seconds. In this problem, you're not really solving any physics related problem where you're understanding how the system works and so on. Instead, you're just going to apply what we've found here. So if the position vector is given by this, then the velocity will be given by this, and the acceleration will be given by this. You're just going to apply that to this. Go ahead, pause the video, and come back. I'm going to now solve the problem. Okay, so let's look at what we have. Question asks you for the velocity and acceleration. These are by definition vector quantities. If I had asked for the speed, then you'd have to find the velocity vector and then obtain the magnitude of this component squared and this component squared. Why is that the case? That's because these unit vectors are perpendicular to each other, and therefore it is square root of component 1 and component 2. If they were not perpendicular, then you would have to go with the dot product and so on, which then has to include the angles and so on. Okay, let's do this now. So we know that we can obtain r dot by differentiating this. We can obtain theta dot by differentiating this. Further, for the acceleration, you will have r double dot and you have theta double dot. So it's a good idea to go ahead and just differentiate what is provided to you. So theta being 0.2t plus 0.02t cubed means theta dot is equal to 0.2 plus 0.06 t squared, and theta double dot would be equal to 0.12 t. Similarly, here we have r given to you as this. R dot would be equal to 0.08 t, and r double dot would be equal to 0.08. Okay, so we have a position vector given as 0.2 plus 0.04 t square in the ER hat direction. ER hat is always radially outward, remember that. There's a magnitude that's given to you and you have it in the direction of ER hat. Okay, now velocity. This, if you just search on Google, you will always find this as the equation, the formula that you can use for finding the velocity in polar coordinates. You don't have to remember this, you should just know how it applies to the coordinate system. Okay, so you have r dot, r theta dot. We just apply it now. This here is r dot, that's 0.08 t along ER hat, plus you have r 0.2 plus 0.04 t square times theta dot, which is 0.2 plus 0.06 t square, this much along E theta hat. Okay, now what does the question ask you? It asks you at the time of 3 seconds. So you just have to substitute t is equal to 3 and you will obtain 0.24 ER hat plus 2.002 E theta hat. It's just a matter of substituting t is equal to 3 in these positions. Okay, what about acceleration? It's just a matter of substituting this for r double dot and all the other components. So you have 0.08 minus r being 0.2 plus 0.04 t square times theta dot squared, which is 0.2 plus 0.06 t square whole squared, this much along ER hat, and then you have along E theta hat 2 r dot theta dot plus r times theta double dot. All of that is along E theta hat. And now if you have to substitute time t is equal to 3, you would then get minus 0.227 ER hat plus 0.557 E theta hat. All this problem did was introduce you to what all of this really means when you apply it to obtaining the velocity and acceleration. Remember always that if the position vector r is given by this much times er hat, then the velocity is not just the differentiation of this along er hat. You also have to account for the rotation of er hat, which is what you obtain here. Sorry. Okay. Let's do another problem. Sorry. In this case now, you have a radar system. So you have your radar tower. And this here is my sketch of a radar antenna. It is capturing at some angle theta currently. There is a rocket that is going vertically upwards. And it is known that at theta is equal to 60 degrees, the distance that's given by r is equal to 9 kilometers. It's known that r double dot is 21 meters per second square, and theta dot is equal to 0.02 radians per second. Okay. This is for a vertically fired rocket. Now the question asks you to find the magnitude of acceleration and the speed of the rocket. Isn't this a useful application? If you think about it, you have a physical system that can calculate, that can obtain whatever is the radial distance. You can obtain r dot, r double dot. You have theta, and since this theta is obtained by some, is generated by some motor that is rotating your radar tower, you also have theta dot and theta double dot. At the moment, the question only provides you at this given theta, at this given distance, r double dot is this and theta dot is this. You have to use this to find the speed and the magnitude of acceleration. Okay. The clue here is that it's a vertically fired rocket. Okay, that kind of constrains what is the actual velocity of this rocket. It is going to be in this direction. Acceleration is also going to be in this direction. These are your clues. Now try and attempt to obtain the answer for what is the magnitude of acceleration and speed. I will now solve the problem. I hope that you paused and then you tried to solve this yourself. Okay. So essentially, we don't know what is the velocity, that is v. We know that there is an angle theta from this radial position. This here is theta. And that theta is 60 degrees. So to be a little more accurate, let's draw it in this way. This here is your 60 degrees. And then according to our polar coordinate system, we have a component of velocity that's going to be in the radially outward direction, right? And that component is given by r dot er hat. So this here is r dot er hat. And there's another component that's perpendicular, which is in this direction, which is given by r theta dot e theta hat. Okay, this is just writing down the clues that are given to us. How to make use of this? What are known to us? We have theta known, we have r known, we have theta dot known. We don't know what is r dot. Okay, can we find what is v at this point? Again, if you got this far, I hope you are able to now make use of the trigonometric properties to then see that this velocity v has two components, this one and this one. Can you find an angle here? Yes. This angle here is equal to 60 degrees. This is perpendicular to this. It's 90 degrees, right? So this has to be 30 degrees since these two add up to 90 degrees. So if this is 30 degrees, then this must be 60 degrees. Okay, so we have the angle between this and this, and as we just saw, we know r, we know theta dot. So what is r theta dot? That's given to us as 9 times 10 to the power 3, it's 9 kilometers. Theta dot is given to you as 0.02 radians per second. Okay, so you want to keep the units consistent. When in doubt, always move it to a consistent unit, so SI units in this case. Essentially, the component of V that is 60 degrees apart. So the component of V along the E theta hat direction is basically V cos 60, right? So V cos 60 is equal to this over here. That is 9 times 10 to the power 3 times 0.02. Does that make sense? I hope so. The component of this along this direction is V cos 60. Okay, that's all I did. So with this, we have V is equal to, if you were to divide by cos 60, you will get 360 meters per second. So in this way, by making use of our radar system, you're able to calculate the speed of this rocket. Let's try that again for acceleration. It's the exact same idea. So in this case, we used the component of velocity to find, using the polar coordinate system, we're able to find the velocity. Let's apply the same idea to acceleration. It is a vertically fired rocket, and so again we have acceleration as some unknown, but it's vertically oriented. What is the component along the radial direction? I could just have a copy of this here, and in the radial direction, you have a component given by r double dot minus r theta dot squared. Is along ER hat. Why is it in this direction? It's because radially outward from your point of measurement. And then you have another component that is in this direction, perpendicular. Why is it in this direction and not in this direction? That's because theta is being measured from the ground, positive upwards. And so it's positive counterclockwise, giving you this as the direction of increasing theta, which is what I now mark as my E theta hat. So if I were to write down the components, it's essentially 2 r dot theta dot plus r theta double dot. That gives me 2 r dot theta dot plus r theta double dot is along E theta hat. Okay, let's look again at the problem. What components do we have? We have r double dot, we have r, and we have theta dot, which means then that we can obtain this entire magnitude, which is nice. Similar to what we had done earlier, this angle is 60 degrees, right? So this one has to be 30 degrees, which now means that A cos 30 is equal to r double dot minus r theta dot squared, which is 21 minus r being 9 kilometers, theta dot is 0.02 the whole square. This gives you acceleration A is equal to, and you now substitute cos 30, you divide that, the right side with that, and you should get 20.1 meters per second square. Okay. Um, I hope this makes sense. Let's do a similar problem, except we're going to make use of some more clues in a very similar problem. So now the next problem, and of course you can pause the video to evaluate whether you've actually got this or not. You're now tracking a fighter jet, or just any jet that's traveling horizontally, and your radar system is here. It is looking at this jet, and in this instance, you have given only a few components. That is, you have theta being measured in this way. The height is 3 kilometers, and this radial distance is 5 kilometers. So essentially, theta is not given directly, but you could obtain it. Um, I'll write the question now. The radar system is tracking its position and finds at a distance of 5 kilometers as shown. Theta dot is equal to 1.72 degrees per second, and theta double dot is equal to 0.78 degrees per second squared. Now the question asks you what is the jet speed and magnitude of acceleration. Okay, again, pause the video and try to solve this. It's very similar to what you just did here. Okay, so how do you approach this problem? This requires a little more understanding of the clues. So it tells you that the jet is traveling horizontally. It doesn't really say if it's traveling rightward, but you have that theta dot is positive, which means that this theta is increasing, which will only happen if it is going from this to this, right? So this here's theta, theta increasing means it would be positions going in this way, which means it's traveling rightward. Okay, so that is one clue which tells you that the velocity is rightward. So this here is the velocity, which is unknown. Now we have that there are components according to the polar coordinate system. So there is one component that's radially outward. That would be in this direction, radially outward. So that is this component here. And that component is given to you as r dot er hat. Okay, so that is r dot er hat. And then there's another component that is a transverse direction. So is it going to be in this direction or is it going to be in this direction? It has nothing to do with the velocity. It has to do with how theta is being measured. Theta is measured positive in this direction, which is different from the previous problem. But essentially, in that direction of increasing theta, you have your transverse component, which is r theta dot. I always like to verify it. No shame in that. It's r theta dot e theta hat. So that gives you r theta dot e theta hat. And okay, that now gives you the component, but do you have the angle available to you? This theta over here is somehow, it's either here or here, right? Which one is it? So if you were to look, essentially, let's just copy this here so that we have it readily accessible. This angle here is going to be 90 minus theta, right? Which means this is also 90 minus theta, which means this here is theta. This is 90 minus theta, which means this is also 90 minus theta. So this here is theta. Okay. So what does this allow us to write now? We have the component of velocity in this direction is essentially v cos theta is going to be equal to r theta dot. Then we have v sine theta is equal to r dot. Which among these is available to you? Do you have the radial distance? Yes, there's the radial distance. Do you have theta dot? Yes, it's given to you. Do you have theta? Well, yes, you do actually have theta because this is a hypotenuse and this is the adjacent side. So cos theta is equal to 3 by 5, which means I could write v cos theta being 3 by 5 is equal to r being 5 times 10 to the power 3 times theta dot is 1.72. If you were to write this, you would make a grave mistake. And the reason is that it needs to be in radians per second, but was given to you in degrees per second. How do you convert degrees per second to radians per second? Try to recall, don't do a Google search. Essentially, 180 degrees is pi, right? So 1 degree would be pi over 180. So this here is how 1 degree would be converted into radians. So if you were to now change your degrees per second to radians per second, all you have to do is divide by, multiply by pi by 180, and this gives you radians per second. With that, you've safely taken care of all aspects in this problem with so many clues that you have to account for. And so now you will get v is equal to 250 meters per second. Nice number. Let's now try to do acceleration. In this case, again, theta double dot is positive, which means that the acceleration is also rightward. So we have acceleration A, and there's a component that's radially outward, again in this direction, whose magnitude is, as we saw previously, r double dot minus r theta dot squared. And then you have another component that is along the tangential direction, whose component is given by 2r dot theta dot plus r theta double dot. Now we want to apply a similar kind of idea where we have the component of A being this and the component of A being that. So we have A cos theta is equal to 2 r dot theta dot plus r theta double dot, and A sine theta is equal to r double dot minus r theta dot squared. I hope that makes sense. So do we have everything that we're looking for? So we had r, we have theta double dot, we have theta dot, we don't have r dot. Okay, what about the right hand side? We don't have r double dot, we have r, we have theta dot. So are we stuck because we don't have r double dot, we don't have r dot? Can we do something? Here's a clue. V sine theta is equal to r dot. So essentially, we can have this r dot defined as v sine theta, which now allows us to use this relation here. So you have 2 times v sine theta, theta dot plus r theta double dot is a cos theta, which if you were to now substitute all the values, you get again a times 3 over 5 is equal to 2 times, if you were to do 250 sine theta, it'll be, in this case, this would be 4. So 4 over 5 I mean, how's it for? You can just use Pythagoras to do it, or you can get the exact theta using the cos inverse and so on. However way you do it, you will get that V sine theta is equal to 200. And then you have theta dot given to you as 1.72 times pi over 180 plus r is 5 times 10 to the power 3. Theta double dot is 0.78 degrees per second square. So you have to again multiply it by pi by 180 to convert it to radians per second. With this, you will get A is equal to 133 meters per second square. Okay. So this, I hope you can see, is like they're playing a game. You have a bunch of clues that are given to you. You're trying to make use of it to then obtain something useful. Okay, let's do another problem where we have a car that is running right. Sorry, an athlete is running rightward. Um, I'll write the question down. So we need a figure to be able to get this, because one clue is in the figure. Um, basically have that person is running along this track here, and the person is here currently, and this is how theta is being measured. And we have theta dot. I'll also provide you this distance as 20 meters. Essentially, this here is your video camera. And it's given to you that this is 10 meters away. Okay. So the question says that this video camera that's tracking the athlete is rotating at theta dot is equal to 10.5 degrees per second, and the athlete is currently at this position, 20 meters away rightward and 10 meters away downward. What is the athlete's speed? Again, pause the video and try for yourself. So I'm going to solve it now. You have the velocity being rightward, again unknown. You have a component that's radially outward, that is in this direction, right? And that component radially outward is r dot, er hat. And then you have a component that is in the transverse direction, that's given by r theta dot. Why is it in this direction? That's because that is the direction of increasing theta. Okay, where's the angle theta appearing here? So this here is 90 minus theta. This being 90 means this here will be theta. So this here is angle theta, which then means that we can write that V cos theta is equal to r theta dot. V sin theta is equal to r dot. Which among these can we use? First, can we obtain what is cos theta? Yes, it will be this distance divided by that distance. That's easily calculatable. You have r. Yes, again using Pythagoras theorem. Theta dot is given to you. Just be careful, it's in degrees per second, which means we can use this here. So what is R? That is root over 10 squared plus 20 squared, which should give you, I believe, 22.4, giving me also that cos theta is equal to 10 over 22.4. And with that, I can use V cos theta is equal to R theta dot, which is 12.5 times pi over 180, giving me V is equal to 10.98 meters per second. So that is again how you can obtain the speed from just knowing the information about how this tracking device is rotating and what is the radial distance. Okay, I hope this makes sense. Let's do one more problem. So you have, let's set some reference frame here, and this here is your reference frame at a distance of 5 meters, and at an angle theta being measured this way. Here you have that this is 4 meters. Okay, so of course you can find now what is this radial distance. There is this point particle that is known to have a speed of 10 meters per second in a direction that's given by 30 degrees. Okay, so what are r dot and what is theta dot? So in this case, we're given the speed, we're given the angle, and the question asks you what will be r dot and theta dot. So as this particle is moving in this way, how will this r change? And as it does so, how is theta going to change? Always you want to have a sketch that helps. So let's do that sketch now. Do you have the angle? This here is 4, this here is 5. If you were to do, essentially this is tan inverse of 4 over 5 would give you theta. So this is 38.7 degrees. And you have that there's a speed of 10 meters per second at an angle of 30 degrees. What is the radial unit vector? It would be in this direction. And what is the transverse unit vector? It will be in this direction. So this here is E theta hat. This here is E R hat. Okay, what can we do now? Can we find the components along these unit vectors? Yes. At this point, I believe I've given enough hints, so you can try and solve this yourself. Pause the video and try to obtain the solution. What is r dot and what is theta dot? Okay, so how do you solve this? You have the velocity component along the ER hat direction is going to be equal to R dot, which is going to be equal to this component is going to have a negative value. You need to find what is this here, right? So you take this speed and then you take the obtain the component here, which means you need to know what is this angle over here. Can you find that? Essentially, this 38.7, this 90, which means this entire angle here is 90 minus 38.7. So 90 minus 38.7 is equal to this 30 plus this unknown angle. So 30 plus unknown x, giving you x is equal to 21.3 degrees. So essentially this gives you that r dot is equal to minus 10 cos 21.3. Why is it minus? Because ER hat is outward pointing while this velocity vector is in the opposite direction, as in the component is in the opposite direction. That's why you have a negative sign there, from which you then obtain R dot is equal to minus 9.31 meters per second. Similarly, along the E theta hat direction, you have R theta dot is equal to, so that's along this direction. Again, you have a negative sign and you're looking for this component, which is going to be minus 10. So this here is your vector. You're looking for this component. That's going to be sine of 21.3, which gives me r theta dot, where r is equal to root of 4 square plus 5 square. Right? This distance here is the hypotenuse. This is r theta dot is equal to minus 10 sine 21.3, giving me theta dot is equal to minus 0.568. It's going to be in radians per second. Okay, so I think we've done quite a few problems on polar coordinates. I hope you understand why this is useful. In the next session, we're going to look at a special case where the radial distance remains fixed. Think about what kind of motion that would be. Thank you.